want to give your hardware the ability to see, whether you're building a ground station to track racing drones or a smart gimbal for your quadcopter, the math is the same. Today we're building the computer vision brain to make it happen. This system uses a standard webcam with Python code to lock onto the objects I choose. I click the mouse, the computer calculates, and it sends the coordinates to the Arduino. This is part 1. Today I'm going to show you the brain of the operation, the Python code that powers the computer vision. I'll walk you through how to set up the tracker, how to map the pixels to servo angles, and how to communicate with hardware without crashing your code. Let's dive in. Before we look at the lines of code, let's understand the logic. It's actually simpler than it looks. For the input, we grab a video frame from the webcam. For the processing, we use OpenCV to find our object. It gives us an X and Y coordinates of where the object is on the screen. For the translation, this is the tricky part. The screen is in pixels, say 0 to 640, but the servo speaks in degrees from 0 to 180. We need to do some math to convert them. For the output, we send those angles over a USB cable, which is a serial port, to the Arduino, which moves the motors. With our libraries, CV2 is OpenCV, serial is for talking to the Arduino, and NumPy helps with the math. I've set up a configuration section here. Notice the use servo flag. This is great for debugging. If you don't have your Arduino plugged in yet, you can test the vision system without errors. Connecting to hardware is risky. Cables get loose. I wrap the connection in a try except block. If the Python script can't find the Arduino, it doesn't crash. It just prints a warning and runs vision only mode. Always code defensively. So OpenCV has changed a lot over the years. Some of you might have an older version, some the new one. I wrote a function called createTracker that acts like a compatibility checker. It tries to load CSRT first. CSRT is incredibly accurate but slightly slower. If you need pure speed, you can uncomment the KCF lines, but for a turret, I prefer CSRT because it handles shaky movement better. And if those two don't work, it will fall back to the MIL, which is what we're going to be using for today. So next we have the mouse handler. So how does the code know what to track? We use a mouse callback. When I click the left button, it grabs the X and Y coordinates of my cursor. It creates a 60 by 60 pixel box around that point. It tells the tracker, this is your target, don't lose it. Next we have the main loop. So I wrapped it in a while true loop, and here's the magic. Inside the while true loop, we get the center of our object, but we can't send pixel 300, for example, to a servo. So I use something called np.interp, which is numpy interpolation. So if the object is at, for example, pixel 0, which is to the left, the servo goes to 180 degrees. If the object is at pixel 640 to the right, the servo goes to 0 degrees. So it handles all the scaling for us automatically. Finally, we send the data. I formatted as a string, pan angle and tilt angle. I also added a safety check here. Uh, if the Arduino disconnects mid-operation, a burnout for example, the try except block catches it, so your program keeps running instead of freezing up. Okay, so let's see it in action one more time. As you can see here, I'm not connecting it to an Arduino, so it will say Arduino connection failed, running in vision only mode. And we gotta wait for it to run. Okay, so now it opens this. And if I try to track this object, it says here, click to lock. So when we lock on that object and we try to move it, you'll see that it follows it. And it creates a path behind the object. So here I'm using the MIL tracker. As you can see here, it works perfect. So we have a working brain, but the brain needs a body. In part two, we are going to jump into the hardware. I'll show you the Arduino code to parse this data, how to add the servos to an external power supply, and how to assemble the pan tilt mechanism. The code for this video is linked in the description below. Download it, install OpenCV, Contrib, Python, and see if you can get the green box tracking on your webcam. If you like this breakdown, hit the like button and subscribe so you don't miss part two. We will make this thing move. Thanks for watching and happy coding.